Good afternoon. I'm happy to be here. Actually, I'm honored to be here and be part of such a spectacular program. I want to thank David and Thea and Steve for putting this all together, and all the other folks who've worked so hard for this. This is just a great event. I also, in the interest of full disclosure, I need to make a confession as well. I'm completely terrified at giving a talk in front of this group, so you'll have to bear with me. Anyway, I was asked to talk about air quality and air pollution. And today in the U.S., we often take the air we breathe for granted, but air pollution is really an important societal issue. And one of the reasons why I'm very interested in this is because I think science has and will continue to have a strong influence on air quality management in this country and other countries. So today we're celebrating the 50th anniversary of the Hubbard Ecosystem Study, so it's appropriate that we talk a little bit about air pollution. We've heard a lot of that from other talks earlier today, so it's an important theme. And in particular, Herb Borman, we're having these Herb talks. He was a great friend and mentor. Herb had a keen interest in air pollution effects on ecosystems, so I'm pleased to have the opportunity to dedicate this Herb talk to his memory. So air pollution, a little bit of background information. Air pollution is not a new problem. There are very early references to air pollution that date back to the Middle Ages when King Edward I banned the use of coal and lime kilns in London in 1307. The modern era of air pollution, dates back to the middle part of the last century. There were several severe air pollutant events. Have any of you heard of the town of Donora, Pennsylvania? I see a few nods of the heads and raising of the hands. So in October 1948, this small town of approximately 14,000 experienced a severe air pollution event occurring over 4 days, resulting in the mortality of 20 individuals, and over a third of the town experienced illness from this event. There was a similar event a few years later, 1952, in London, causing 4,000 events. So these and other events really galvanized the clean air movement in the U.S., which led to the original Clean Air Act and the later groundbreaking 1970 and 1990 Clean Air amendments to the Clean Air Act. The Clean Air Act has done some remarkable things. It's established what are known as criteria pollutants. Criteria pollutants, which are sort of shown here on this slide, are contaminants of national concern, things that we've heard about today, things like sulfur dioxide, ozone, particulate matter. The Clean Air Act not only established these pollutants, but standards for these pollutants to address local air problems like were experienced in Donora, Pennsylvania. There are two types of air standards. There are primary standards that are set to protect human health. In fact, they're designed to protect the most sensitive individuals. And then there's something known as secondary standards. And secondary standards are established to protect human welfare. Now you might ask the question, and it would be a very good question, what is public welfare? Public welfare. What is public welfare? Well, it's everything else but human health. So it's the side of the building, it's crops, it's ecosystems. So it's all other things. So although we have both primary and secondary standards, which you see here, it's interesting to note that when secondary standards have been established, they are always the same or higher than the primary standard, okay? And so the way I interpret that is, as the Environmental Protection Agency, which sets these standards, sees it, we humans are the most sensitive entity with respect to air pollution. So are we really the canary in the coal mine when it comes to air pollution? So it's something to think about. I don't want you to get the wrong impression though. Air quality management in the US and in Europe for that matter has been wildly successful. There have been marked improvements over the last 40 years. If you look at this slide from the EPA, you see a number of metrics for economic development. Things on the upper panel here, such as gross domestic product, population, energy consumption, over the last 20 years have all increased, while the criteria pollutants, this aggregate of criteria pollutants, have been markedly decreased, as we've heard about. So air quality management in this country has effectively decoupled economic development from air quality, and this, in my mind, is a remarkable accomplishment. Air quality programs in the U.S. have focused on the protection of human health. This is not a bad thing. There are some humans I like, so it's good to protect them. It's been assumed that atmospheric emission control programs that are designed to meet primary health-based standards will have a co-benefit or trickle down and also protect ecosystems. And this has, in part, been correct. So, for example, we've heard about earlier today that we've had controls on sulfur dioxide and nitrogen oxide emissions from power plants, decreases in acid rain, and improvements in terms of surface water quality. A great example of this are data right here at Hubbard Brook. This is a slide showing you concentrations of sulfate, nitrate, pH, and some other things, acid neutralizing capacity in aluminum from Watershed 6 at Hubbard Brook. These upper three data are Gene's data starting in 1963, so this is a 50-year record, a remarkable record of water quality, and it tells us volumes about how the ecosystem is responding. Okay, so we see these decreases in sulfate over time and a little bit more erratic, but also decreases in nitrate, and we see this increase in pH from relatively low values, very acidic streams, to now streams that are less acidic. So we see some recovery. These latter two panels, these represent my data sets, acid neutralizing capacity in aluminum. So I started here, a lot of people think I'm an old timer. I started here actually in the 70s, but we started these measurements in the early 1980s. So you see my records pale in comparison to Gene's records of 50 years, but they're still about 30 years, so they're something. But acid neutralizing capacity is considered to be a valuable and important metric of the acid-base status of waters. And it's hard to see trends here, but if you look very carefully, and we know the folks in the front row are paying attention, that the values were low, actually negative values to start, and they've been slowly but steadily increasing over time. So there is recovery. The recovery is occurring at a relatively slow rate. This last panel is aluminum, and aluminum was something that I got involved in to look at here at Hubbard Brook with Noy Johnson. I was honored to have the opportunity to work with Noy. Great, enthusiastic individual, and he was very excited, geologist or scientist, very excited about aluminum. And so looking at the inorganic fraction of aluminum, that form is toxic to fish and other aquatic organisms. I've got a little red line here to indicate what's thought to be the toxic level of this inorganic form of aluminum. And back in the day, in the early 80s, the concentrations were very high, well above levels that would cause fish toxicity. And if you look at the decreases, they are just remarkable to very, very low levels today, actually fairly close to the analytical detection limit. So there have been some successes, particularly on surface water quality. But unfortunately, as we've heard from John, there have been some lingering effects of atmospheric deposition. Atmospheric deposition has acidified soils and eutrophied ecosystems, and these delays are due to the legacy of air pollution effects. So we have sort of a disconnect here in terms of the recovery of the systems. We have the human health effects and we have ecosystem effects, and we see some differences in the extent and level of change in terms of changing air quality and air quality control programs. And I think this is largely due to the difference in the mechanisms by which we're exposed to air pollutants. So we humans, we're exposed to the concentrations of air pollutants that we breathe. We take them in, we experience the effects of that ambient air. If it improves, then there can be improvements in human health. Ecosystems are a little bit different. They're really concerned about the deposition of these materials. The materials that are raining down on the land surface, the precipitation, the gases and the particles. And not only what's going on instantaneously, but that cumulative long-term deposition which occurs over decades and decades and decades. And the effects that we see are manifested in this. So we see materials such as sulfur, nitrogen, and mercury this working still? Oh, okay. Are accumulating in soil. And eventually, when soils get saturated, these materials are mobilized and leached into surface waters. And then some of the acids, sulfuric acid and nitric acid, they will carry important nutrients like calcium, magnesium away from them and deplete from soils. So these processes are experienced over very, very long periods of time, and so the effects are very difficult and slow to recovery. And so we see the effects, long-term effects on ecosystems such as the forest effects that John talked about. Okay, so where are we with this and where am I going? That's a very good question. First of all, I want to tell you, in recent decades, air quality management in this country has shifted from the local problem that we saw in Denora to a more regional focus. So we focused on sulfur dioxide, particulate matter, ozone for human health, visibility, and deposition of sulfur and nitrogen and mercury for ecosystems. But increasingly, our current and future air quality problems need a multi-scale, and by multi-scale I mean local, regional, and global perspective, a multi-pollutant, and a multimedia approach in management. I want to go back to another example of sulfur dioxide. This is a slide showing you sulfur dioxide emissions globally over the last 150 years or so. The upper panels, the upper lines here, the brown and the red, represents emissions from North America and Europe. And you can see the effects of the Industrial Revolution and the air control that we've been talking about, marked increases in sulfur dioxide emissions, and then these huge drops since the 1970s, a remarkable accomplishment. But if we look at the rest of the globe, we see a different perspective. We see that many other countries are showing marked increases in sulfur dioxide. Sulfur dioxide is really a local or regional pollutant, has a residence time of a few days in the atmosphere, so it's manifested through local and regional air quality problems. So the types of air quality problems that we experienced decades ago are being experienced today in these developing areas. Okay, increasingly we're becoming concerned with air pollutants that have longer residence times. There are many, these are global pollutants, and many of them have linkages among the atmosphere with the oceans and the land. Good examples of this include things that we've been talking about: carbon dioxide, methane, and mercury. Mercury is something that I'm particularly interested in, and I couldn't get away without talking a little bit about mercury. Okay, mercury is a global pollutant. This is a slide showing the historical emissions of mercury. The upper panel is sort of by source, and the lower panel is by region, so they're color-coded, and they start out in the mid-1800s and proceed out today. So the pattern of mercury emissions is very interesting. It was very, very high back in the 1800s associated with mining activity. Mercury mining, gold mining, silver mining in North America, South America, and Europe were very important mercury emission sources. Those largely dropped down, and in the 1900s they were replaced largely by coal combustion. Again, very high levels in North America and Europe. Those have dropped down in recent decades due to the air quality controls that we've heard about, but they've been replaced by these very large increases in coal emissions in Asia in recent years. Okay, so the problem is solved, right? At least locally, right? Isn't that the case? So why should we care? Well, the rub is that once mercury is released from geologic reservoirs, it persists at the Earth's surface for centuries. That's right, I said centuries. Okay, so it's around for a long time. So right here we're pointing the finger at Asia. It's very easy to point the finger at Asia. We do it a lot. But in the case of mercury, it's only part of the problem. The current emissions, which are very high in Asia, are clearly a problem. But what is more problematic is the long-term release of mercury to the environment. So although Asia is currently responsible for 65% of our direct human-based emissions of mercury to the atmosphere, only 30% of deposition is from Asian sources. And the reason for this is because this legacy of mercury emissions. So if we look in the panel on the left, these represent the best guesstimates of mercury emissions to the atmosphere. You can see that there's about 13% natural. These are from volcanoes and such. About 27% from primary emission sources. These are today's release from power plants and mining activities and other things. And 60%, a whopping 60%, is from these legacy sources. So of the 350 gigagrams of mercury that have been released all time, only 50 has gone away, has been sequestered. 300 gigagrams are still roaming around in the oceans, in the terrestrial system, around for us. So again, why should we care? So that's always a good question. My students always ask me, who cares? Why do I care? Well, the reason why we care is because our exposure to mercury is largely through consumption of fish, primarily ocean fish and fish from the Pacific Ocean. This is one of the reasons why the United Nations Environmental Program has developed a global mercury treaty that's going through countries for ratification as endorsed by the State Department. More and more, our view of what is air pollution is broadening. As a result, our management perspective needs to broaden. In addition to criteria pollutants and hazardous pollutants like mercury, which were focused in the 1990 Clean Air Act amendments, we have carbon dioxide, methane, nitrous oxide, the new kids on the block that are now considered to be air pollutants by the Supreme Court and the EPA, and we're having discussions, as we just heard about from Fred, on how to control these emissions. Changing climate clearly influences air pollutants, particularly things like mercury and ozone, and air pollution is a multimedia problem. Ecosystems are affected by air pollutants. In the late 1980s and early 1990s, Europe was out in front of the world and developed a program called critical loads to guide emission controls to protect ecosystems. Today in the US, the Forest Service and the Park Service have embraced the use of critical loads to protect public lands. Critical loads are really just another form of secondary air pollutants. And this approach in air quality management needs to be expanded in the US. Developed countries have greatly improved air quality, resulting in tremendous benefits for human and ecosystem health. Future air quality management will need to take a more holistic approach. We will need to consider local, regional, and global transport and management of air pollutants. We will need to address not only linkages among air contaminants, but also the interactions with changing climate and land use. We're not the only entities that interact with our one atmosphere. We need to manage it wisely. And I know this is a little bit out there, but just in the interest of bringing a little bit of the arts in here, and I'm going to play for you a little bit, not much. Steve will give me the hook. This opus by Julius Hempel called One Atmosphere, if the audio system works. Steve gave me the hook, so I'm turning it off. We can listen to it later. Okay, any questions?
I learned there's a new rule for emceeing around here. You get blamed for everything.
That's the rule, yes. I thought you always got blamed for everything.
Well, that's true. I can't, sorry. We got a John.
So how are critical loads different from secondary standards, or are they just the same thing with a focus on the ecosystem?
Well, they're a little bit different. Actually, the EPA went through an assessment of secondary standards, a combined standard for nitrogen oxide and sulfur dioxide a couple years ago. And the way, as I understand it, I'm not a lawyer, but as I understand the way the Clean Air Act is at least interpreted, it needs to be a concentration-based standard. So critical loads are really a deposition-based program. So the loading of a material, which will protect ecosystem health. So you need to be below this loading. And what the EPA did was they have actually developed a big conversion factor across the relevant portion of the area to translate the ambient air concentration with what would be the equivalent deposition in that area. I think that's kind of a stupid way to do it, but that was the way they had to do it. But basically they were interpreting that as an approach for the secondary standard. It was ultimately the administrator decided not to go that way, but it's through a 5-year cycle and it may come up again. And as I said, that the Forest Service and the Park Service have been very aggressive in putting together these deposition-based approaches to protect ecosystems.
Charlie, I wonder if you could just tell us a bit more about the inorganic aluminum decrease. How much of that is due to changing pH versus changing DOC? And so what has total aluminum done, dissolved aluminum done in that period of record?
Okay, well that's a great question. It's a little bit different depending on where you are in the Northeast.
Just restate it.
Oh yeah, sorry. So the question by Bill McDowell was, could we talk a little bit more about the changes in aluminum? Could we talk a little bit about the changes in total and how has that changed, and what are the patterns for the organic fraction of aluminum in addition to the inorganic fraction of aluminum? Hopefully that's a good interpretation of your question. Hubbard Brook is a watershed that's relatively low in concentrations of dissolved organic carbon, at least the watershed 6. And most of the aluminum is in an inorganic form. There's been no statistically significant decrease or change in the organic form, although now it dominates the form. So originally, back in the day, in the 80s, it was very much overwhelmingly inorganic. Today, that's gone down very low. It's mostly organic. In other regions of the Northeast, there have been increases in dissolved organic carbon, and we see coincident some increases in the organic fraction of aluminum. And those sites elsewhere in the Northeast, we've seen also pretty much universal decreases in the inorganic, which is thought to be the toxic fraction of aluminum.
And could that lead to
All these questions on aluminum, I can't believe it. Yeah, go ahead, Mark.
could that lead to the phosphorus being released in the algal blooms of the stream?
Well, there's a lot of discussion about that. There were a lot of, back in the day, acid rain day, there were a lot of interesting hypotheses about aluminum driving controls on carbon and controls on phosphorus, and a lot of those have resurfaced. And I think part of the problem is we don't have, across a lot of systems, really good long-term records of phosphorus. But I think that is a viable hypothesis. We are seeing increases in chlorophyll in many systems that's coincident with this. And so I think that's a real, viable hypothesis, frankly. I don't think we have good measurements now, and maybe we need to do some experiments, but I think that is not an unreasonable thought. Yeah.
Hey, Charlie, so it seems to me that the science regarding a one atmosphere is obviously pretty clear. Perhaps less clear on a policy front. The question I thought I was thinking about your Mercury results and your science there is how is the science about tracking depositions from emissions? And is there a way to really tie deposition events with emissions elsewhere in the world that might in turn try to upclose the no understanding at more of a policy level?
Well, that is a very, oh yes, yeah. Okay, so a little bit on the science of mercury emissions, and are we able to track sources of mercury to try to, I think Fred said talked about the success of the sulfur trading program. And I think part of the reason for that, in addition to what he said, it was really having those monitors on the facilities, that you had those measurements that were right there in the public eye. And I think, unfortunately, I think for mercury, it's a little bit more challenging. Hopefully, we can go there, but Most of the mercury that's deposited, at least in this part of the world, is dry deposition. So it's mostly gases and particles, very hard to measure. Generally, the models to track emissions and models are used to track emissions and deposition. I think they're very poorly constrained for a number of reasons we could talk about for quite a long time. But I think there is hope on the horizon. There are a number of stable isotopes for mercury. There's we have a prominent stable isotope scientist here. Joel Bloom was doing a lot of work on sources of mercury. He's been using these approaches to track feeding areas of certain types of tuna that are high in mercury and looking at where they're getting their mercury, and he's looking at the possibility of looking at stable isotopic sources. So I think, it sounds like science fiction, but I think it's not outside the range of possibilities, but it's a huge challenge. I said today most of the emissions are thought to be from coal combustion, but artesian mines are very, very poorly constrained, but are thought to be a very, very high emission source, but very, very high uncertainty. So there's a lot of problems in terms of mercury, particularly in developing countries, in tracking emission sources.
All right, one last question.
I wonder what you just say a little bit about black soot and its role in the whole air quality question.
Well, probably Steve knows more about black soot than I do, but yeah, it's I didn't mention it, but it's certainly a material of concern. I don't know, are there good trends information about black carbon? And I think it's just recently been identified and quantified in terms of its role in terms of forcing greenhouse gases, and so I think it's very much an area of focus, but I don't know of good time series data. Do you?
No, there has been a couple. There's a recent Bond et al. That's a good summary of the state of the science. The challenge for black carbon is also just doing some of the basic physics. Not all black carbon was created equal. Black soot. So you have brown soot, you have black soot, you have everything in between. Its physics are different, and so it's a real challenge figuring out. And it's because of just like the deposition, the particle size variation affects where it's transported to and how it interacts with the atmosphere. So regrettably, it's a complicated issue. There's some indication it could be an incredibly important short-term forcer, but that's contested science. That's not well established yet.
So how do you stack it up with the other pollutants he's been talking about today?
From human health standpoint, I'm not a human health person, it's really big. There's some great studies in New York City and elsewhere showing that traffic-generated black carbon particulate soot, the PM 2.5, it can be incredibly harmful. So recently, New York City banned use of number 6 oil, which is one of the few places in the country. If you ever drove New York and you'd see these big puffs of black smoke coming out of buildings, that was number 6 oil when the furnace came on, the boiler came on. That act in 10,000 buildings in New York City, banning the use of number 6, will half the amount of particulate matter in the city, because it was greater than the total amount generated by automobiles and truck traffic in the city. So that's a specific locality, and that argument, we had a lot of discussions about the climate impacts. We said, you don't even need to make those. The health impacts are so large, we just win it on health, and we can still have our science debates about how important that was from a climate standpoint. Thanks. Sure. Sorry about that.